All right, in this video, we're going to take a look at motion along one dimension. So you all know the 3 dimensions, and we're just going to look at motion in one dimension. So let's take a look at this train. So the train in this picture is in Bosphal, India. I've never seen a train quite this crowded in China, but it's pretty common in India to have trains this crowded. Now, this train, if we make some observations as good scientists, and I ask you what direction it's moving, you have 2 choices, right? The train could either be moving this way, or it could be moving this way. Well, if you notice the way the people on the train are looking, people tend to look or sit in the direction of motion. We can deduce that the train is moving this way. This is a one-dimensional motion. The reason it's one-dimensional is because the train is on a track, and that track limits the motion to only one direction. So I could ask, how fast is this train moving? And there are actually quite a few answers that you could give me. And the reason is this: if you told me the train was going 160 kilometers per hour, that would be a possible answer. If you gave me that answer, you'd have to tell me a frame of reference. So for example, the train is moving in this direction at 160 kilometers per hour. With reference to, and the way we show with reference to is WRT. With reference to tells us a point of reference that we can observe the train from. From the ground would be a point of reference. So this guy who's not on the train, he sees the train zoom by at 160 kilometers per hour. So we could say with reference to the ground. Well, let's imagine that instead of on the ground, there was somebody on the moon, and they had a giant telescope, and they could look at this train on their telescope. And I asked them, how fast is this train moving? Well, they're on the moon, so they would not give me the same answer. They would not say 160 kilometers per hour, because they're not only seeing the motion of the train on the Earth, but they're also seeing the motion of the Earth as it rotates. And so they would have to give me a much bigger number. The Earth rotates at about 1,600 kilometers per hour. So if you were on the moon, you would see the train moving at about 1,760 kilometers per hour. And of course, this is with respect to the moon. So depending on your frame of reference, you can get 2 very different answers for the same situation. Let's talk a little bit more about frames of reference. So let's watch a short bit of this video called Frames of Reference. This is one of the best physics videos I've seen. I watched it in high school, and I'm going to share it with you.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
So let me introduce a physics term, our first one really, other than frame of reference, and that is displacement. So the displacement of an object is a line drawn, or the distance of a line drawn from the initial position to an object's final position. So if you imagine, here's a gecko, maybe the one from the commercial, maybe not, and it starts at this position here, somewhere around 22 centimeters. And it moves in a straight line to about 85 centimeters. The displacement of this gecko is defined as delta x, or in other words, this delta in physics means change. And it's called delta. The Greek letter delta means change. So the change in displacement is equal to the final position of an object minus its initial position. So x sub f and x sub I. So this is our first equation. So some examples of displacement would be our track runner that goes all the way around the track. It goes all the way around the track once. 400 meters is the distance, but their displacement would be 0 because they start at 0 and they end at 0. Displacement is known in physics as a vector quantity. So this is another word, another physics term, and a vector quantity involves both magnitude and direction. So what this means, any vector number in physics can be a positive or a negative value, and the negative doesn't means direction. So for example, if we look at some of these pictures here, if we remember the equation for displacement is final position minus initial, here the ball goes from 10 to 80. In this case, it would be 80 minus 10. It would have a displacement of positive 70. But let's say, for example, the ball started at 80 and went back to 20. So here, the final position would be 20. The initial position would be 80. It would have a displacement of negative 60. So I could ask you, which ball moved further? This ball moved 10 centimeters further. It wouldn't be 130 centimeters further. The negative here just implies the direction. So based on these examples, these two examples, the positive sign means to the right, the negative sign means to the left. So it is possible to have both positive values for displacement, as you can look here, and negative. And I'll leave you with one more question to think about. And you can, maybe in class tomorrow we can talk about this. In track and field, are the races, which are the 100 meter, 200 meter, 800 meter, I forgot the 400 meter, 1600 meter, and 3200 meter dashes. Are these labeled in terms of their distance or their displacement? If you said their distance, you're correct. These are all regarding the total distance run. Some of these, but not all of them, if they were labeled correctly in terms of their displacement, would be labeled as 0 meter dashes. Can you think about it and tell me tomorrow in class, which of these wouldn't be labeled as a 0 meter dash? See you tomorrow, and remember, physics is fun.